This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Friends are not able to make it to today's lecture, please maybe take a copy for them or snap a photo for them as well. Alright, so it's my last lecture today, but it's not the last lecture for potential flow. So next week you'll still be having potential flow lectures. Right, but what I normally do at the end of potential flow is give out these handouts. Actually I should, can it be? Thanks. I've printed 100 copies of this, and there's supposed to be 200 people in this class, but I'm getting extra, so I guess some of you did not make it to lectures. Thanks. And if you don't have a copy, just, cheers. All right, I'll just put it here. If you want to grab one for your friend, just grab a couple as well, okay? Couple of these. Yep. Have a couple of these, that's right. Right, so it's just to summarize, I guess, the material that we have learned in the past 5-6 weeks. So we have learned quite a bit, right? There's quite a few derivations and quite a few important concepts. So I've just summarized them here. It might not be complete, so please feel free to add other derivations which you should, I guess, know, right? Especially when you're revising. Yep.
I want to ask about the lecture notes.
Yep.
Do we have to go over them, or the presentation is enough?
I think the lecture notes are quite similar to the presentations, to the lecture slides. So I would go over the lecture notes. I think most materials should be in the lecture notes as well. And there's some exercises on in the lecture notes, so please do them as well. Yeah, there's quite a few exercises there. Right, so just a summary of a few derivation, important concepts which you should know. And if you flip behind here, you'll see that there's a bunch of boxes which are empty, which hopefully when revising, you should be able to fill them up. Right, so for instance, I'll go through the first line here. So definition. So if you look at a stream function, you should know that a stream function automatically satisfies continuity, right? Okay, and only satisfies your momentum equation when the Laplacian of psi is equals to 0. All right, and you can fill it up for your potential function and your complex potential and so on and so forth. Okay, and also there's some example flows which we have gone through in the lectures: uniform flow, sink source, doublet, potential vortex, so on and so forth. And you should, I guess, you are expected to know how to write the stream function, potential function, and the complex potential for all of these flows. And at least kind of know how to sketch these flows as well, right? So I hope this piece of paper would be useful for you guys. And if you haven't received a copy of it, just feel free to grab a few more for your friends who are not around. Okay, so the next thing I'd like to talk about is for the assignment. Right, I'm just going to show you what to do and what not to do in the assignment. So here we have our question 1E, right? And your plot should look something like this when using the Euler's method. Okay, please don't have this kind of legend. This legend doesn't tell me much. All right. You should have a legend telling me what step size is for this particular case, for the different colored lines, basically. Right. And if you're using an RK4 method, you should get a plot that looks like this. Okay, and the legend here is quite, I guess, clear. So when it's red, h, or my step size is equals to 0.1, and blue is when it's 0.001, so forth. Okay, so you should get something that looks like this. Everyone get something that looks like this in your plot? Yes? Yep, or you haven't done it yet? Haven't done it yet? I hope you guys have done question 1E. Right. Next is for the smoker's problem. Okay, so if you error trap based on proximity, based on the distance from your sink, okay, you get a nice result which looks like this. Okay, and these are all your streamlines from the source coming out to the sink. Okay, and if you do not error trap, you're going to get something that looks like this, a spidery graph. Okay, and you will be penalized for that. Okay, so please use some error trapping to prevent the singularity at the sink. Okay, and also when you're plotting the streamlines, for the smoker's problem, it should look something like this. I've used black lines for the streamlines coming out from the source and entering the sink. Okay, and all the other streamlines entering the sink are in gray. Right, so it looks a bit nicer. So I can differentiate the flow a little bit. I've plotted my stagnation points in red here, these red dots, okay, clearly. And all the lines going through my stagnation points are my separatrix, right? And I've plotted them in red. Okay, so all of these are my separatrix lines. Okay, and if you have a nice plot like this, then you'll get full marks. All right. Okay, so continuing with our lecture. So we had a look at the pressure distribution for flow over rotating cylinder. Okay, and in this case, flow is moving from right to left, and it's rotating anti-clockwise. So we know that the velocity at the top bit here is going to be very, very high, which means that our pressure is going to be very, very low. Pressure coefficient is very low here. It's negative here compared to the bottom. And that will give us a net lift upwards. Okay, and we found that lift is just a function of your density, your free stream velocity, U infinity, and also gamma, which is your circulation of the potential vortex. Okay, and this rotating, and this lift caused by the rotation of the cylinder is known as the Magnus effect. And I showed you a few examples where they have rotating, these weird-looking rotating cylinders on ships, also on planes. And this is a very bad example of a design of an airplane which you do not want to sit on, for sure. Right, and also in, I guess, wind turbines. Okay, but the topic for today's lecture is on conformal transformation. Right, and this is a very important concept which we'll be using to convert our cylinder into an airfoil. Right, so finally we're going to get a flow wire and airfoil, and we're going to calculate the drag on the airfoil. Okay, so that's what we're going to be doing for the next few lectures. Okay, so what's a conformal transformation? So a conformal transformation is basically a transformation which preserves all angles from the original plane. Okay, so here you can see that in the Z plane here, the blue lines are always perpendicular to the red lines. Okay, and if I apply some transformation, okay, where now in the Z plane is just equals to Z squared, sorry, Z1 plane is equals to Z squared. Okay, so now I'm going to have this you're going to have something that looks like this in the Z plane, Z1 plane, right, where it's warped. Okay, and you can see that the angles between the blue and red lines are still 90 degrees in the Z1 plane. Okay, so therefore this transformation, which is known as warping, is a conformal transformation. Okay. Now, if I apply some transformation where Z1 equals to Z plus I times Z minus the conjugate of Z. Okay, so this transformation is known as shearing. Okay. Is this still a conformal transformation? No, yeah, the answer is there. So it's not a conformal transformation. All right, because you can see that the angles between your red and blue lines are no more 90 degrees. Okay, so this transformation is non-conformal. Okay, but we're only interested in conformal transformations in this course. Okay, and you'll see why we're interested in a few slides' time. Okay, so let's imagine the blue lines are lines of constant psi and the red are lines of constant phi. Okay, and since they're orthogonal in the z-plane, I get this relationship here, right? Can you tell me what's this special relationship here? The Cauchy-Riemann equations, right? So we can write the equations in this form. Very good. Okay, and if angles are preserved, they must remain orthogonal in the Z1 plane, in the transform plane. Okay, which means that in the Z1 plane here, I can write my Cauchy-Riemann's equations as well, but this time in the Z1 plane. Okay, so we have x1, y1. Right, so therefore, if the Laplacian of psi and phi are satisfied in Z, my original plane, okay, and if I apply a conformal transformation, this then tells me that the Laplacian of psi and phi are also satisfied in the Z1 plane, okay? Right, so it's quite easy to prove this. So if angles are preserved in the transform plane, Z1 plane, okay, and if I calculate the Laplacian of psi, okay, I can then swap this term here, psi del x1 with del phi del y1, right? And del psi del y1 with del phi del x1. Okay, and if I put it in, you can see that the Laplacian of psi is equal to 0. And similarly, I can show that the Laplacian of phi is also equal to 0. Okay? So this is very important because it means that all my governing equations, right, my continuity equation and my momentum equations are satisfied in the Z1 plane if they are satisfied in the original Z plane, right, before the transformation. Okay, everyone clear so far? Yep. So we're going to learn a few different conformal transformation, which is going to be important. So the first one is rotation. Okay, so in the transform plane, Z1 is just equals to Z plus exponent of negative I theta. Okay, so please take note of the negative here, right? And theta is just measured from the horizontal. Okay, right, so first one is rotation, which is very important. The next one is translation or bodily shift. Okay, so in the transform plane, Z1 is just equals to Z plus x naught plus I y naught. Okay, and x naught here is just some shift in the x-axis, and y is some shift in the y-axis. Okay. Right. The next transformation, which is crucial, is the Joukowski transformation. Okay, and this was introduced by Nikolai Yegorovich Joukowski. Okay, and there's no correct spelling to his name, actually. Okay, you can see that his name is Joukowski with an I, Joukowski with a Y and U with an I. You can get Joukowski with a ZH, U, right? And combinations of W, I, and Y, okay? And that's because Joukowski is a Russian, right? So his real name is that. Okay, that's his real name. Have you all heard of Joukowsky before? Have you all heard of him? No? Ah, okay. So he's actually a very, very famous person in aerodynamics, right? Very respected person in aerodynamics. And apparently, he's also very famous in the moon. There's a crater named after him as well. So he has contributed a lot in developing airfoils, and yeah, and they're going to learn his transformation. All right, okay. So the Joukowsky transformation is not too complex. All right, it's basically saying that Zj, so J is just the transformation. The Joukowsky, it's the plane after the Joukowsky transformation. All right, is equals to Z plus C squared over Z. Okay, and Zj is just the transform coordinate. Right, now if I substitute Z with X plus IY, okay, and I'm just going to multiply this term here with the conjugate X minus IY. Okay, and I can then split up these terms into real and imaginary terms. Okay, and I find that the axis xj equals to x1 plus c squared over x squared plus y squared. And in j here, sorry, in the y-axis, j equals to y1 minus c squared over x squared plus y squared. Okay? So if we have a circle in plane Z, what shape will I get when I apply the Joukowsky transformation? Can anybody guess? Square? No, not square. Right? So if you had a circle in plane Z, right, where x squared equals to, sorry, x squared plus y squared equals to r squared, okay, I can then substitute r squared into those two terms on the left and right, okay? And I can then rewrite my terms of x and y. Okay, so x is now xj over 1 plus c squared over r squared, and j is just, sorry, y is just yj over 1 minus c squared over r squared. Okay, and if I substitute back into an equation of a circle, what does this look like? An ellipse. I heard someone say an ellipse. All right, and you're absolutely right. Okay, it's going to become an ellipse. Okay, so a circle in your z-plane will be an ellipse in the zj plane after applying the Joukowsky transformation. Okay, so this is really, really important to note. Okay, so this is your major axis, all right, where it's r plus c squared over r, and your minor axis is when r minus c squared over r. Okay, now what that constant we have c is basically our Joukowsky circle. Okay, it is just some constant, a Joukowsky circle. And r is the radius of your cylinder. Okay. Now, what happens if I increase my Joukowsky circle C so that it approaches R? What's going to happen to this term here when C is equals to R? So it's going to be R minus R, which is 0, right? So this here would approach, I guess, infinity, right? And here you'll get something which approaches 2R, right? Correct. So basically, when my Joukowsky circle C approaches R, I'm going to get my minor axis to approach 0, okay, and my major axis to be twice the length of the radius. Okay. Right. And you can see I get a flat plate. Okay. So my cylinder now has transformed into a flat plate. Okay? Now, if let's say R is much greater than C, right? Or if C is very, very small, you can see that these terms here, they go to 0, and it basically approaches a circle, all right? So the transformation has no effect on the so the effects of transformation is not really felt, okay, when C is much smaller than R. So if you look here, when your radius of your cylinder is very large, right, in the transformed plane, it still remains, I guess, a cylinder, okay, when R is much greater than C, okay. But when C is, I guess, quite close to R, right, you get almost something which looks like a flat plate. It approaches a flat plate. Okay, so you should be able to know the limits when R equals to C, sorry, when C equals to R, and when R is much greater than C. Okay, all right, so when we differentiate the Joukowski transformation with respect to Z, okay, we get something quite interesting. Right, so if I differentiate this, Z is just going to be 1, and C squared over Z is just going to be negative C squared over Z squared. Okay. Now, there's going to be a problem when Z equals to 0, right? So when Z becomes 0, this term blows up here. Okay, so there's a singularity. Okay, but this is not very important because when Z equals to 0, it's inside of the body, inside of the solid body. So it's we're not too concerned about that. All right, but we do see that there are two critical points, okay, when dzj over dz equals to 0. Okay, so when this term here equals to 0, what we see is that you're going to have z equals to plus minus c. Okay, and c is a real number, a real constant. Therefore, we have two critical points at x equals to plus minus c. Okay, and this is quite interesting because what it tells us is that a smooth curve passing through these critical points, they become corners in a transformed plane, right? It become very sharp corners. Okay, and for the Joukowski transformation, smooth curves passing through these critical points will form a cusp or knife edge in the transformed plane. Okay, so let's have a look what happens. So here I have my Joukowski circle, C. Right, and as I increase C, it becomes, or it approaches a flat plate with a length of 2r. Right, twice its length. Okay, but now when I fix C and move my circle, okay, so C is fixed here and I'm moving my circle. When my circle here touches the Joukowski circle, when my cylinder touches the Joukowski circle, look what happens in the transformed plane. Right, you can see that we now have a very sharp or leading edge at this point here, due to the critical points, right? When x is equals to plus minus c. Okay, and this, I guess, looks like a symmetric airfoil, right? We get something that looks like a symmetric airfoil. Okay, right? And if I change the radius of my circle or my cylinder, right, you can see that the ratio between the cylinder radius and the Joukowski circle governs the thickness to chord ratio of our airfoil. right? So you can see the thickness to chord ratio changes as I change the radius of my cylinder. Okay, and it becomes thinner and thinner. Now, the next thing that I can do is shift this circle, okay, in the y-axis, in the imaginary direction. Okay, so I'm moving it up now. I'm moving my cylinder up, and you can see that it then gives me a cambered, it creates a cambered airfoil or an asymmetric airfoil. Okay. Right, so I have a short, I guess, MATLAB code to show you. Okay, so if you have a look here, this red line is my Joukowski circle, okay, and the blue is my cylinder in the untransformed plane, and applying the Joukowski transformation, I'll get an ellipse, right? And all right, and I can move my cylinder around. Okay, so you can see that as I move my cylinder closer to the Joukowski circle, right, I'm going to get a very sharp leading edge or trailing edge at the left-hand side, okay, of my airfoil, right? And if I move it to the right here, now my sharp leading or trailing edge is on the right-hand side. Can you all see that? Right? Okay, and if I move it upwards, right, I'm going to create camber. Okay, now I'm just moving it upwards and it's not touching anywhere, right? And you can see I just get a camber in this shape. Okay, but to have that sharp leading edge, I have to ensure that my cylinder is touching the Joukowski's circle, right, to get this sharp trailing or leading edge. Okay, you always want to make sure that this is touching. Okay, is everyone okay so far? Is everyone following? Yes? No? Maybe? All right. So the Joukowski transformation is just very simple, right? The maths is not too difficult. It's just z plus c squared over z. But you can see that it gives you a really, really nice result, especially for us who want to figure out the forces around an airfoil. Okay, so therefore, if I want to get a flow around an ellipse, okay, all I have to do is to calculate the streamlines for the flow around a cylinder, right? You always start with a flow over a cylinder, okay, as such, okay, and next is just to apply the Joukowski transformation to the streamline coordinates. Okay, and I get the streamlines for a ellipse, a flow over an ellipse. So you all have, I guess, developed your RK4 codes, right? And all we have to do is just start off with streamlines for a flow over a cylinder, okay? Which you can do very easily in MATLAB, right? Okay, and to transform these streamlines into the Joukowski plane, okay, all I have to do, right, is just say that Zj is equal to z plus c squared over zj. Sorry, I think that should be z. That should be z. Okay, and all you have to do then is just to plot the real, which is going to be your x, and the imaginary, which is going to be your y. Okay, and you'll see that your streamlines will become will be transformed to streamlines for a flow over an ellipse. Okay. Right, so now I've changed my constant c to be equal to the radius of the cylinder, right? So my Joukowsky circle is now equal to the radius of the cylinder. Okay, and that's just going to give me a flow over a flat plate, right? And you can see that my streamlines are all just straight, right? This flat plate is not affecting my streamlines at all. Okay. Now, what I can do next is I can also easily rotate the flow around the cylinder by 90 degrees. Okay. So remember, we have this rotation, this conformal rotation, right? Which is just Z1 equals to Z exponent negative I times theta, where theta now is just pi over 2, right? So we have rotated it by 90 degrees. Okay, so if you plot Z1, the streamlines of Z1, okay, this is going to be our flow over a cylinder with flow coming from bottom to top, I think. It's probably top to bottom, but just check it out, right? So next, okay, after applying a rotation, what I can do next is I can apply another transformation, right? And now I want to apply the Joukowsky transformation so that I can get a flow over a perpendicular plate. Okay? So now here I've applied the Joukowsky transformation on Z1. Okay? Not on Z, but on Z1, which is the field which we have already rotated. Okay? And if I have a look at the streamlines now, I'm going to get a flow over a flat plate. Okay? Right. So that's for a flow over a flat plate. Okay? And you know, since we know what the streamlines are, we know what the velocities are, okay, we can then very easily calculate our pressure coefficient. Okay? Right, so we know that in the z-plane, our velocity is just u minus iv, right, when we differentiate our complex potential. And in the zj plane, it's similar, right? dw dzj is just equals to uj minus ivj, right? And that's your velocities in the transform plane, whether it be a flow over a flat plate, flow over an airfoil, or whatever. Okay? And through the application of the chain rule, okay, you know that dw dzj is just equals to dw dz, okay, which is your complex potential in the untransformed plane, times dz dzj. Okay. Right, so basically, if I want to find my velocities in the transformed plane, it's just going to be equal to my velocities in the original plane, okay, multiplied with dz dzj. Okay, and dz dzj here is just a multiplying factor. Okay, and typically when we are calculating the pressure coefficient, we only need the velocity magnitude, right? We're not really looking at the vectors. We only need the velocity magnitude. So I can rewrite it as Vj, right? Our velocity magnitude is just equals to V times the absolute of dz dzj. Okay. Right. So just an example here. So if we have a flow over a cylinder, we know that V is just 2u infinity sine theta, right? Which is just our azimuthal velocity, right? There's no radial velocity. Okay, and we know that dz, the magnitude of dz over dzj is just equals to 1 over dzj over dz. Okay, and we know what dzj over dz is. Okay, we can very easily calculate it. So we just have to differentiate our Joukowsky transformation. Okay, which is just 1 minus c squared over z squared. Okay, so all I've done is I'm plugging this into here. Sorry, I'm plugging this whole thing here, 1 over into here, and this term here into here. Right? So I'm going to get Vj is just equals to 2 u infinity sine theta divided by the magnitude of 1 minus c squared over z squared. Okay, and I can then substitute this result into our pressure coefficient equation, which is just this one here. Okay. Right, and there are some elegant analytical solutions to flat plate problems, but you can compute this curve numerically. Okay, so if I plot the pressure coefficient, you can see that it will look a little bit different in your transform plane for this flow over an ellipse. Okay. Now, there is a bit of a problem though. Okay. So the problem arises is when dz, j over dz has 2 critical points, right? Remember? What are the critical points? Z equals to, or x equals to, plus minus c. C, okay. Right, exactly. So what's the problem with that? Because when z equals to plus minus c, this term it goes to 0, right? And what happens to your velocity in the transform plane? It goes apeshit or infinite, right? Right. So that's not good. So that's not good. Okay, so to get a cylinder to touch the Joukowski's, we need to get the cylinder to touch the Joukowski circle, right, to get our sharp trailing edge for the airfoil. Okay. So the question then is, what should I do to stop Vj here from going infinite? What do you think I should do to prevent this velocity here from blowing up? So this we know is going to approach 0. So we only can do something about this. So what must we do about V? So that this doesn't go to infinity. So this has to go to 0, right? So we want this term here to approach 0 faster than this term approaching 0. Okay, basically. Right? So let me give you an example. So if let's say we have a flow over a cylinder, okay? We start off with a flow over a cylinder, and I want to have an angle of attack. Okay, so my first transformation is to rotate the flow by some angle alpha. Okay. Right. So this is my transform. Okay. And then I want to apply the Joukowski transformation with C equals to A. Right, so my Joukowski circle is just equals to the radius of the cylinder, and that will give me a flat plate. Right, so I will get a flow that looks like this. Okay, so a flow over a flat plate at some angle of attack. Okay, so remember there is some problem here, right? Because if you look at this flow here, your trailing edge here, your velocity is not 0, which means that your velocity at your trailing edge is infinite. Right? So that's not good. So to make sure that this velocity here is doesn't go to infinity, we want to make sure that our stagnation point occurs at the trailing edge. Okay? We want to make sure that our stagnation point here occurs exactly at the trailing edge. Okay, and that's known as the Kuta-Joukowski condition, right? You guys might have, I might know this guy, this Martin Wilhelm Kuta, right? And it's from the RK4 method, right? Right, so the Kuta-Joukowski condition basically states that a body with a sharp trailing edge, which is moving through a fluid, will create about itself a circulation of sufficient strength to hold the rest stagnation point at the trailing edge. Okay, so there's a lot of words, but for us it basically means that all we have to do is just adjust the circulation around the cylinder. Okay, when we adjust the circulation around the cylinder, we can then adjust the location of the stagnation points so that it lies on the trailing edge. Okay, so to satisfy the Kuta condition, okay, we start off with a flow of a cylinder. We apply an angle of attack. Next is we adjust the circulation of the stagnation. Sorry, we adjust the circulation so that the stagnation point is at the trailing edge. Okay, and then we apply the Joukowski transformation. Okay, so have a look here as I change my circulation, or as I change the strength of gamma. Okay, what do you think is going to happen to these stagnation points here when I change gamma? It's going to go down, right? And I want to make sure that this stagnation point here lies exactly at x equals to negative c. Okay, so I'm going to change my circulation. There, all right? And you can see that in my transform plane, the stagnation point now lies exactly at the trailing edge of my flat plate. Okay, so if you have a look at this this photo here, you have a flow over an airfoil, right? And you can see that your stagnation point occurs exactly at the trailing edge for this particular case. Okay, are there any questions? All right, so if there's no questions, that's all for today's lecture. And next week, we'll continue looking at the flow over an airfoil and also looking at how you can calculate the lift and drag for an airfoil with an angle of attack. Okay, thank you. And those of you who have not taken one of these cheat sheets, just feel free to come in front and grab one. Oh, thank you, thanks. Yeah, grab a few for your friends as well. Because we have one up here. Yeah. Good.
Yeah, so the thing which you showed us now before the negative 2.
Oh yeah, cool. Grab as many as you want.
How you modify the trailing edge at that point?
Yep.
But the leading edge also goes down.
Yeah.
That isn't proper as well.
So that's not correct as well for a flat plate. Yep. But for a airfoil, that's not so important, right? Because for an airfoil, yeah, so you're right. So there is also some infinite velocity here for this particular case. But for an airfoil, that's not the case, right? Because only one side is touching. Here it's not touching. So
so then that will remain the same.
then that's okay.
Okay.
But for a flat plate, yeah, there's probably more elegant solutions for flow.
So like there are better solutions than this guy? For
Sorry?
the flat plate? Are there better solutions than
Yeah,
Joukowski?
I think so. Well, Yeah, for flat plate, I guess it's quite simple. There's a lot of people who solve it, but yeah, it's probably not covered in these lectures. But where is it? I think in the lecture notes. Yeah, there's.
Yeah.
You can maybe see pages 93 or 94 in your lecture notes. Yeah, but
And camber, is it asymmetric airfoil? Like,
camber, yep. So if your airfoil is curved, right, you have some camber basically. So people use camber so that you can increase its lift.
okay, increase, but then would it, like, you can't apply, is it applied in cars as well? Aerodynamic cars? Like,
Cars, camber cars, I guess is a tires. It's a bit different.
okay.
Yeah, tires, right?
Because I've heard cambered cars. But then if you increase lift, then it's not supposed to, like, it can't function as a car, right?
Yeah, I think camber, the word camber basically means just off axis. Yeah, so in airfoils, camber means, I guess, it's asymmetrically shaped. And it's supposed to, I guess, give you better lift characteristics while maintaining similar drag penalties. Yeah, so you get more lift for the same drag, basically, if you have camber. Yeah.
And for the research, like, what
Yes.
do I...
Andrew's still away, but maybe later in the semester we can have a chat some more. Yeah. What do you have any particular interests?
Aerodynamics.
Maybe remind me at the end of semester again.
Okay, yeah.
Yeah. But I'll definitely inform Andrew. She's coming back next week, but I'll be away next week.
You're going back home?
No, I have a conference, so I'll be away for.
So aerodynamics, something, what's it?
Yeah, it's a turbulence conference. I'll be away. But definitely, yeah, keep in touch.
Sure.
Do bug me on email.
Yeah,
Then I will.
definitely. Yeah. Thank
Okay,
you.
it's good. It's good.
Thank you.
From the lab section.
Lab section. Okay.
Yeah, so
Well,
I like to integrate the force.
oh, is this a lab question?
Yeah.
Sorry, I can't do lab questions. I'm not very good at it. Yeah.
Problem is
Yeah.
about the integration. So when we calculate the fx is this way, so we integrate the force from here minus this force from here. The code.
Is it? Trap Z, right? You just use C.
Yeah, trap Z. So this tab 7 to tab 23 minus.
You have to separate it.
Yeah, but
Okay.
but my question is, if we have if the angle of attack is not zero, like this way, and the flow is like this way.
How do you know where you cut it, right?
Yeah, it's not just this simple. It's because
Yeah.
I look into our data. So when the angle of attack is like this one, like 20 degree, the force on the plane is.
You have to decompose it into.
So if we still integrate from here to here,
Why? Who asked you to split it up? Don't you just integrate the whole thing? Do you have to split it up? Because you just add a sine theta term, right?
but we need to integrate the front minus the bottom.
To get a drag.
Yeah.
But lift is always perpendicular to your surface, right?
If it is
Sorry, I mean drag pressure is always perpendicular.
Yeah.
Can't you just integrate it with respect to the whole surface? Doesn't work.
but we need the direction.
Oh, I'm really bad in labs. I haven't done this for that for so long. Maybe Ruwan would be a better person to. Yeah, have you asked him? Have you asked him? Is Ruwan your lab?
Yeah,
Just one.
but
He doesn't want to tell you that.
he will not have time today, so
Oh,
make
yeah.
an appointment with him.
Yeah. I think it'd be good to just maybe email him because I don't want to tell you the wrong answer as well. I haven't done this for many years, so the lab might have changed already from since when I did it last time. Yeah, but I would advise you to maybe just email him. Yeah.
Got the answer.
Because by right you shouldn't split it into parts. I think you should just integrate the whole thing. Because you don't know where the flow is separating, right? I would
think?
Yeah, from the data I can see where the flow separating.
Oh, did it tell you?
This is the original data.
Oh.
And this is
What's your report?
CP.
Right.
Yeah, good. The Sierra is, I think it's okay, but the CD of here, 70 degree and 20 degree, it should be higher.
Yeah, I don't know why. I think this is error. There's some error, I think.
So I think the problem is separate.
Yeah, I think there's some error. Or CD just becomes constant. Because here you have your lift dropping, right? So there's flow separation already. Yeah, and then I think drag is just what?
If the drag is still constant, I think it's just
Constant.
a little error.
Yeah, I think it should be constant. Because this is CD, right?
Yeah.
Sorry. But your drag force might be higher. Is it? Yeah, because this is CD, right? So CD equals to force, drag force,
Yeah, force,
divided by half rho u infinity A. So here your A is smaller, is bigger, so your force might be bigger, right? That's why it gets lower.
So this is
It's reasonable. It should maybe be about constant. I think it's reasonable. Maybe. I think it should be okay. But it's experiment, so there is bound to be error. So in the discussion, you just explain what are the possible errors that you have in your experiments. It could be reading the pressure tubes. There could be many errors, right?
yeah, a lot of error.
Yeah. too many errors. So, yeah.
Thank you.
Yeah. Okay, no problem. Yeah. Sure.
There's one
Uh-huh.
tutorial
Yes.
that if you do the math, you get if k equals to this. I forgot this expression.
Yep.
It's basically if this vortex is
Very
not,
strong.
it's not. If it's not very strong, the streamline is just this, and then it just avoids the vortex, right?
Yep.
And then if the vortex is very strong, it becomes like this because the separator is now here and here.
That's right.
But when it's exactly one, it's exactly here. And I thought it was going to be like perfect circle like this, but it's actually like it makes a turn like that.
Oh.
What happens here? And then like, how do I deal with this? Explaining this.
Why is it not a circle?
Yeah, because it's a circle here, right? And then it touches here, and I thought it was a circle. I thought it was a circle, but when they did tutorial, it becomes like it's not a circle anymore.
Yeah, because your velocity, right? Your potential vortex, as your velocity goes further and further away, your velocity becomes less and less. Yeah, so I think that's why it doesn't form a perfect. It's not a perfect circle. It's going to change. If it's a circle, right? Then when you calculate the streamline, it should be a constant here, right? It should be the equation of a circle, but you don't get it. Yeah, but do you have so when drawing this kind of images, right? I think it's good to start up with you got your velocities, you got your stagnation points. Separatrix, do you have an equation for separatrix for this?
Yes, I can get it. I don't have it now, but I can get it.
Yep. So maybe that will help you, I guess, to I guess draw the streamlines a little bit. Yeah, but if it looks okay, I will normally give full marks in the exam. I won't penalize you if this is not straight or if it looks similar, I will be happy. Yeah.
So if there is a stream going here, will it go through this? It will go through.
So that's the thing. So if you draw this, okay, you need to draw also the direction of your streamlines. Then I'll give you full marks. So this case, this streamline should be going in, right? This streamline looks like it's going out. This one's going out. This one's going in. This one's going in, and this one's going out.
Okay.
Yeah.
And if it's here, it's going to be like this.
Exactly, right? So that's why it has to go through, right? Because if this streamline, is going this way, you cannot have this streamline going.
Yeah.
Yeah.
Facing each other.
Yes. Opposite each other. Yes. So then you get to guess, I guess, how long it looks like. Yeah.
A bit freaked out, but
It is quite challenging, that question. Yeah. But it's good that you're looking at it.